Hello students, welcome in your classical mechanics class. In this lecture we will talk about the Kepler's law. We know in Kepler's law we have three laws: first law, second law and third law. So first we look at the statement of Kepler's law. So Kepler's first law is Kepler's first law states that all the planets revolve around the sun. I write it. All the planets revolve around the sun in an elliptical path with sun at one of the foci of the elliptical path. We will prove it later. And Kepler's second law is the position vector of the planet with the sun sweeps out equal area in equal time interval. That is, the areal velocity of the planet is constant. This is second law. So what is this areal velocity? As you know in your junior classes, what is the definition of velocity? Velocity is time rate of change of displacement dr upon dt. And as we are talking about the position vector of the planet with the sun sweeps out equal area, that means instead of this displacement we have dA upon dt. So in that case this velocity is areal velocity, change in area with respect to time, you can say like this. So that means the area covered per unit time, you can say the area covered per unit time, that is the areal velocity is always constant. And third law is the square of time period of planet, the square of time period of planet, that means if t is the time period, then t square is always directly proportional to q of semi-major axis of the ellipse or elliptical orbit of the elliptical orbit around the sun. That means t square is directly proportional to a cube. A is the semi-major axis as we represented in our previous lecture. And now we will look at the proof or the deduction of Kepler's law from the study of motion of body under inverse square force field. As in our previous lecture on inverse square force field, we find out that eccentricity is represented by small e is equal to square root 1 plus 2e L square upon mu k. That was the expression we find out in our previous lecture. Mu k square. As the system, that means the sun and the planet, they are bounded in a system, and in a bounded system the energy E is always negative. So the negative value of total energy of the body or the planet follows that there is something which is subtracted from 1, so that small e is always less than 1. And we find out that if eccentricity is less than 1, then the path or the trajectory is elliptical in nature. So that was the statement of first law. All the planets revolve around the sun in an elliptical path with sun at one of the foci of the elliptical path. Sun will remain at one foci, as in the elliptical orbit or the path there are two foci and sun is at one foci. So in the second law, as we know, the path is elliptical. So let it be an ellipse. This is the semi-major axis. There are two foci and sun is at the one foci. So let it be sun, and planet is at some point A. Now, as the planet revolve around sun in anti-clockwise direction, so suppose at any time t the position vector is r, SA is r, and in small time interval dt the planet reaches at point B, so the position vector is now dr plus dr. So this dr is AB. So this dr is in small time interval t. Now we know this SAB is like a right angle triangle if dr is very small, and if dr is very small, then this portion of diagram is like this. So this is SAB. So we can consider this angle as right angle, and the area of this triangle is DA, because we are considering small area due to small dr. DA equal to 1 upon 2 base is SA into this AB. So this SA is 1 upon 2 R, and this AB is dr. This is DA. Now we know V, if V is the linear velocity, V is dr upon dt. So we can write dr equal to V into dt. So we can write it as 1 upon 2 r cross V into dt. So we can rearrange it as dA upon dt is equal to 1 upon 2 r cross V. Now, as we consider in our previous lecture, there are two bodies having mass m1 and m2, and this is like a two body problem, and we reduce this two body problem to one body problem by introducing the concept of reduced mass, and that reduced mass was represented by mu. So I multiply this expression with mu and divide it with mu. So now it is 1 upon 2 r cross mu v upon mu. So this is r cross mv, that is the angular momentum L. So L upon 2 mu is equal to dA upon dt. So as in our previous lecture we find out that the angular momentum vector L is constant. So if L is constant, 2 is also constant, mu is reduced mass is constant, that means dA upon dt is constant. But in this dA upon dt, A is the area. So rate of change of area with time, that is constant. So that was the definition or the statement in second law. The position vector of the planet with the sun, that means this vector r sweeps out equal area in equal time interval, that is the aerial velocity of the planet is always constant, or you can say that the area covered per unit time dA upon dt is constant, because L, 2 and mu, all these three terms are constant in our expression. So L was the angular momentum of the planet around the sun, and we know that the planet moves under the action of central force, therefore its angular momentum is conserved. This is already discussed in our previous lectures, you can go through those lectures. So vector L is constant, so dA upon dt is constant. So we have reduced the second law of Kepler's law of planetary motion with the help of all these expressions. Now we are looking at the third law. The statement of third law is the square of the time period of planet around the sun is always directly proportional to cube of the semi-major axis of the elliptical orbit around the sun. That means t square is directly proportional to a cube. Now in this elliptical orbit, the area of ellipse is, we know the area of elliptical path is pi a b. Now we are interested in the time period t. So time period is area of elliptical path divided by areal velocity. You know the definition of time period. So from here we have written the expression t equal to area of elliptical path upon areal velocity, and we know the area of elliptical path is pi a b, and this areal velocity is L upon 2 mu. So finally we have pi a b 2 mu upon L is t. So this is the time period. Now we know the semi-latus rectum, that means small l is b square upon a. This is already discussed in our previous lecture. Small l equal to b square upon a. This is semi-latus rectum, and also the semi-latus rectum we have reduced is small l equal to L square upon mu k. So from these two expressions we can find out b square upon a equal to L square upon mu k. So from here we can write the value. So we have b equal to L square a upon mu k square root of whole. So this is b. I will substitute the value. This is 2 pi a mu L a 1 by 2 upon mu k square root of mu k into L. So finally we have t is directly proportional to a 3 by 2. Power is 3 by 2. By squaring on both sides we have t square is directly proportional to a cube. But is a the semi major axis? So that was the statement. The square of the time period of planet is always directly proportional to cube of semi major axis. So that means T square is directly proportional to a cube of the elliptical orbit around the sun. That means T square is directly proportional to a cube. So it proves Kepler's third law. So this is all about the Kepler's law.